Hi everyone, welcome back. In this video, we are going to discuss top data structure interview questions and answers. Let's begin. What is a data structure and why is it important? A data structure is a way of organizing and storing data in a computer so that it can be used efficiently. It defines how data elements are arranged in memory and how operations such as storing, accessing, searching, updating, and deleting data are performed. Without proper data structures, programs become slow, complex, and difficult to manage. The main reason data structures are important is performance. Different problems require different ways of storing data. For example, finding an element in an unsorted list takes more time than finding it in a sorted structure. Choosing the correct data structure can greatly reduce execution time and memory usage. Data structures also help in writing clean and well-organized code. When data is structured properly, programs become easier to understand, debug, and maintain. Almost all real-world systems such as databases, operating systems, file systems, and search engines depend heavily on efficient data structures. In interviews, this question checks whether a candidate understands the foundation of problem solving in computer science. A strong understanding of data structures shows that a developer can build efficient, scalable, and reliable applications. Next question. What is the difference between linear and nonlinear data structures? Linear data structures store elements in a sequential manner where one element comes after another. Each element has a single previous and a single next element, except for the first and last ones. Examples of linear data structures include arrays, linked lists, stacks, and queues. Because data is stored in a straight line, linear data structures are easy to understand and implement. They are useful when data needs to be processed in order, such as maintaining a list or processing tasks one by one. However, operations like insertion and deletion can be slow in some cases. Nonlinear data structures do not store data in a sequence. Instead, elements are connected in a hierarchical or network-like structure. Examples include trees and graphs. In these structures, one element can be connected to many other elements at the same time. Nonlinear data structures are used to represent complex relationships such as file systems, organization charts, or social networks. Interviewers ask this question to test whether a candidate understands how data organization affects performance and problem solving. Next question. What is an array and what are its advantages and disadvantages? An array is a linear data structure that stores elements of the same data type in continuous memory locations. Each element in an array can be accessed directly using an index value. This makes arrays very fast when it comes to reading or accessing data. One major advantage of arrays is simplicity. Arrays are easy to use and are supported by almost every programming language. Because elements are stored contiguously, arrays also perform well in terms of memory access and caching. However, arrays also have limitations. In many languages, the size of an array is fixed at the time of creation. This makes arrays inflexible when data grows or shrinks dynamically. Inserting or deleting elements in the middle of an array is expensive because elements must be shifted. Arrays may also waste memory if the allocated size is larger than required. Due to these disadvantages, arrays are not always suitable for dynamic data. This question tests whether a candidate understands performance trade-offs. Next, what is a linked list and how is it different from an array? A linked list is a linear data structure where data is stored in nodes. Each node contains two parts, the actual data and a reference to the next node in the list. Unlike arrays, linked list elements are not stored in continuous memory locations. The biggest advantage of a linked list is dynamic memory allocation. Nodes can be added or removed easily without shifting existing elements. This makes linked list very efficient for insertion and deletion operations. However, linked lists have slower access time compared to arrays. To access an element, the list must be traversed from the beginning node by node. This results in slower search operations. Linked lists also use extra memory to store references. Choosing between an array and a linked list depends on the problem requirements. Interviewers ask this question to evaluate understanding of memory usage, performance, and a real-world application of data structures. 5. What is a stack and how does it work? A stack is a linear data structure that follows the principle of last in, first out. This means the last element added to the stack is the first one to be removed. You can imagine a stack like a pile of plates. You place a plate on top, and when you remove a plate, you remove the top one first. In a stack, insertion of an element is called a push operation, and removal of an element is called a pop operation. Both operations take place only at one end, which is known as the top of the stack. Because of this restriction, stacks are very simple to implement and manage. Stacks are widely used in real-world applications. For example, function calls in a program are managed using a call stack. Undo and redo operations in text editors also use stacks. Expression evaluation and syntax parsing in compilers depend heavily on stack data structures. One limitation of a stack is that you cannot access elements randomly. You can only see or remove the top element. Interviewers ask this question to check whether you understand basic data flow control and how stacks help manage execution order in programs. Next question: what is a queue and how is it different from a stack? A queue is a linear data structure that follows the principle of first in, first out. This means the first element added to the queue is the first one to be removed. A real-world example of a queue is a line of people waiting for a ticket. In a queue, insertion happens at the rear end and is called an unqueue operation. Removal happens at the front end and is called a dequeue operation. This strict order ensures fairness as elements are processed in the same order they arrive. The main difference between a queue and a stack lies in how elements are removed. A stack removes the most recently added element, while a queue removes the earliest added element. Because of this difference, queues are better suited for scheduling tasks, managing shared resources, and handling requests. Queues are commonly used in operating systems for process scheduling, printer job management, and network data handling. Interviewers use this question to test whether candidates understand ordering logic and real-world usage of data structures. Next, what is a circular queue and why is it used? A circular queue is a variation of a normal queue where the last position is connected back to the first position. Instead of wasting unused memory after dequeuing elements, the circular queue reuses empty spaces. In a normal queue implemented using an array, once elements are removed from the front, that space cannot be reused easily. This leads to inefficient memory usage. A circular queue solves this problem by treating the array as circular. When the rear reaches the end of the array, it moves back to the beginning if there is free space available. This makes circular queues more memory efficient and suitable for fixed size buffers. Circular queues are widely used in real-time systems, buffering data streams, and CPU scheduling. Interviewers ask this question to test understanding of memory optimization and efficient data handling techniques. Next, what is a dequeue and how is it different from a queue? A dequeue, short for double-ended queue, is a data structure that allows insertion and deletion of elements from both ends. Unlike a normal queue, which restricts operations to one direction, a dequeue provides more flexibility. In a dequeue, elements can be added or removed from the front as well as the rear. This makes it useful in scenarios where data needs to be accessed from both ends efficiently. Deques are used in applications such as sliding window problems, caching mechanisms, and task scheduling systems. They can behave like a stack or a queue depending on how operations are performed. Interviewers ask this question to evaluate whether candidates understand advanced queue variations and can choose the right data structure based on problem requirements. Next, what is a tree data structure and where is it used? A tree is a nonlinear data structure used to represent data in a hierarchical form. It consists of nodes connected by edges. The topmost node is called the root, and each node can have one or more child nodes. Nodes that do not have children are called leaf nodes. This structure closely matches many real-world relationships. Trees are useful when data has a clear parent-child relationship. For example, file systems use trees to represent folders and files. Organization charts, XML documents, and HTML structures also follow a tree-based model. One major advantage of trees is efficient searching and organization. Compared to linear data structures, trees can reduce the time required to find elements. Some trees are designed specifically to keep data sorted, which improves performance further. Trees are widely used in databases, compilers, and search engines. Interviewers ask this question to check whether candidates understand hierarchical data representation and why trees are important in real-world systems. Next question: what is a binary tree and how is it different from a general tree? A binary tree is a special type of tree where each node can have at most 2 children. These children are usually referred to as the left child and the right child. This restriction makes binary trees easier to process and analyze compared to general trees. In a general tree, a node can have any number of children. This makes general trees more flexible but also more complex to traverse and manage. Binary trees, on the other hand, follow strict rules that simplify many operations. Binary trees are commonly used in searching and sorting operations. Variations such as binary search trees store data in a way that allows fast lookup, insertion, and deletion. Expression trees are used to evaluate mathematical expressions in compilers. Interviewers ask this question to evaluate understanding of structured data models and how constraints in data structures can improve performance and simplicity. Next question: what is a binary search tree and why is it important? A binary search tree is a type of binary tree with an additional rule. For every node, values in the left subtree are smaller than the node's value, and values in the right subtree are greater. This ordering property makes searching very efficient. Because of this structure, searching for an element in a binary search tree can skip half of the remaining nodes at each step. This significantly reduces search time compared to the linear structures like arrays or linked lists. Binary search trees support efficient insertion and deletion operations while maintaining sorted order. They are commonly used in applications that require frequent updates and quick lookups. This question tests whether a candidate understands how ordering rules in data structures lead to better performance and how binary search trees are used in real-world systems. Next, what is tree traversal and why is it important? Tree traversal is the process of visiting all nodes of a tree in a specific order. Because trees are non-linear, traversal is needed to access every element systematically. Different traversal methods serve different purposes. Common traversal approaches include visiting the root first, visiting child nodes first, or visiting nodes level by level. Each method produces a different order of visiting nodes and is useful in different scenarios. Traversal is important because many tree operations depend on it. Searching, copying, deleting, and evaluating trees all require proper traversal. For example, expression evaluation relies on a specific traversal order. Interviewers ask this question to assess understanding of how trees are processed and why traversal techniques are essential for working with hierarchical data. Next question: what is a heap data structure and where is it used? A heap is a special type of tree-based data structure that follows a specific ordering rule. In a heap, the parent node is always either greater than or smaller than its child nodes, depending on the type of heap. If the parent is always greater, it is called a max heap. If the parent is always smaller, it is called a min heap. Heaps are usually implemented using arrays, not linked structures. The tree structure is maintained logically through index calculations. This makes heaps memory efficient and fast to process. The most important property of a heap is that the highest or lowest priority element is always available at the root. Heaps are widely used in priority queues. In a priority queue, elements are processed based on priority rather than insertion order. Heaps are also used in algorithms such as heap sort, which sorts elements efficiently. In real-world systems, heaps are used in CPU scheduling, task management, and graph algorithms. Interviewers ask this question to check whether candidates understand priority-based data handling and efficient retrieval of important elements. Next question: what is a graph data structure and how is it different from a tree? A graph is a nonlinear data structure that consists of nodes called vertices and connections between them called edges. Graphs are used to represent relationships between objects where connections can be complex and flexible. Unlike trees, graphs do not have a single root node. Nodes in a graph can be connected in many ways, including cycles. A graph can be directed or undirected depending on whether edges have direction. Trees are a special type of graph with strict rules. A tree has no cycles, has exactly one path between two nodes, and has a hierarchical structure. Graphs do not follow these restrictions, which makes them more powerful but also more complex. Graphs are used in social networks, maps, recommendation systems, and network routing. Interviewers ask this question to test understanding of complex data relationships and real-world modeling using data structures. Next question: what is graph traversal and why is it important? Graph traversal is the process of visiting all nodes in a graph in a systematic way. Because graphs can have cycles and multiple paths, traversal is more complex than tree traversal. Proper traversal ensures that each node is visited without getting stuck in infinite loops. Traversal is important for searching nodes, analyzing connections, and solving problems like finding paths or detecting cycles. To avoid revisiting nodes, traversal algorithms keep track of visited nodes. Graph traversal is widely used in applications such as navigation systems, network analysis, and dependency resolution. It is also the foundation for many advanced algorithms. Interviewers ask this question to evaluate whether candidates understand how to explore complex data structures safely and efficiently. Next, what is the difference between breadth-first search and depth-first search? First search and depth-first search are two common graph traversal techniques. Breadth-first search explores all neighboring nodes at the current level before moving deeper into the graph. It processes nodes layer by layer. Depth-first search explores as far as possible along one path before backtracking. It goes deep into the graph before exploring other paths. Breadth-first search is useful for finding the shortest path in unweighted graphs. Depth-first search is useful for tasks like cycle detection and topological sorting. Understanding the difference between these two approaches helps developers choose the right traversal strategy. Interviewers ask this question to test problem-solving ability and understanding of algorithm behavior. Next, what is a hash table and how does it work? A hash table is a data structure that stores data in key value pairs. It allows very fast insertion, deletion, and search operations. The main idea behind a hash table is to use a hash function that converts a key into an index where the value is stored. When a key is given, the hash function calculates a hash code. This hash code points to a specific location in memory called a bucket. The value is stored in that bucket. When searching for a value, the same hash function is used to find the correct bucket quickly. One common challenge in hash tables is collision. A collision happens when two different keys produce the same hash code. To handle this, techniques such as chaining or open addressing are used. These techniques ensure that all values are stored and retrieved correctly. Hash tables are widely used in real-world applications such as databases, caching systems, and symbol tables in compilers. Interviewers ask this question to test understanding of fast data access and how hashing improves performance compared to linear search. Next question: what is collision handling in a hash table? Collision handling is the process of managing situations where two or more keys generate the same hash index. Since multiple keys cannot be stored at the same memory location directly, special techniques are required to handle collisions properly. One common method is chaining. In chaining, each bucket stores a list of key value pairs. If multiple keys map to the same bucket, they are stored in that list. This method is simple and effective, but performance depends on the length of the list. Another method is open addressing. In this approach, if a collision occurs, the hash table searches for another empty bucket using a predefined sequence. The value is placed in the next available location. Collision handling is important because poor collision management can reduce performance from constant time to linear time. Interviewers ask this question to check whether candidates understand internal hash table behavior and performance optimization. Next question: what is a priority queue and how is it implemented? A priority queue is a data structure where each element has a priority. Elements with higher priority are removed before elements with lower priority, regardless of insertion order. Unlike a normal queue where elements follow first in first out order, a priority queue focuses on importance. For example, in a hospital emergency room, patients with higher priority are treated first. Priority queues are commonly implemented using heaps. A heap allows quick access to the highest or lowest priority element. Insertion and deletion operations are efficient, making heaps ideal for this purpose. Priority queues are used in CPU scheduling, path-finding algorithms, and event-driven simulations. Interviewers ask this question to test understanding of priority-based processing and real-world system design. Next, what is a sorting algorithm and why is it important? A sorting algorithm is used to arrange data in a specific order, usually ascending or descending. Sorting makes data easier to search, analyze, and process. When data is sorted, operations such as searching become faster and more efficient. Many algorithms and systems rely on sorted data to function correctly, including databases and search engines. Different sorting algorithms are designed for different use cases. Some focus on speed, while others focus on memory usage or simplicity. Choosing the right sorting algorithm depends on data size and application requirements. Interviewers ask this question to test whether candidates understand the role of sorting in problem solving and performance optimization.